Hello again, this is Galen Pickett, Cal State University Long Beach, Physics 151. Today I want to talk about finding the rate of change of the momentum. That is dp dt. If you can do that, that's 1/2 of what the momentum principle tells you. And sometimes you can use that to figure out what unknown forces are. The thing we've been doing so far is using given forces to find out what dp dt is, but that's another whole way to use these this relationship. So I'll point out that we're talking about section 5.3 in the book. So I'll write that right here, 5.3. So here's three situations that look completely different from a physics point of view. I've got an object that is going around a circle with a constant velocity. It has a radius r and a mass m, and there is some force that's causing it to do that I want to know. Here is a different object, a mass m, that's sitting at rest on some surface. And again, it may not seem like an important thing, but there are forces which are causing it to have that motion. And here we've got an object of mass m that is moving with a constant velocity. Again, we can use the momentum principle to tell us how these objects are moving. We've got two pieces from the momentum principle. A piece that tells me what goes on with the system, and then a piece that tells me what happens from the surroundings. So the surroundings always change the system. That's the way this logically is all set up. So the dividing line between the system and the surroundings is this equal sign. So if I know how the momentum of the system is changing, that can only come from the net force from the surroundings. And that is what the momentum principle says. Here, this object going around a circle, the v has a constant magnitude, but the momentum is pointed in that direction. Once the object gets here, its momentum points in that direction. Once it's here, its momentum is downwards. The momentum of that object as the system is not a constant, and it is caused by something. If we could only see the dots showing where's the object at different points in time, we would see the dots are equally spaced, but they are curving continually. And if I look at, so the question is, what kind of a net force is required to make that happen? Well, it's not speeding up or slowing down, so whatever the net force is, it has to be a vector that points in some direction. It cannot point in the direction parallel to the velocity. If the net force pointed parallel to the velocity, then the object would speed up or it would slow down. So the only directions for this net force can be away, so perpendicular to the velocity, either away from the center or towards the center. And I think from the suggestion of these dots, the only thing that makes sense is that there is a force that points towards the center. And the magnitude of that force, I'm going to call this dp centripital dt. So I know how the momentum changes. That is caused by some net force, and that net force will, it has a size, it has a magnitude, which is mv squared divided by r, and it points in the inward direction. Now we can put a little unit hat over there. So this, whatever the forces are in the surroundings, they've got to provide this, so that we've got the change of the momentum of the system is given by what the surroundings are doing to it. Here we've got a situation where the object is at rest, and you very naturally think to yourself, if the object is at rest, the forces should balance. So I've got dp system dt is equal to 0. So not only is the momentum not changing direction, it's not changing magnitude, that magnitude is 0 all the time, so the net force from the surroundings has got to be 0. So the momentum principle would say, and what are those net forces? Well, let's say I've got a weight force down, and I always know what that is, that's the mg. I've got an unknown force up, n, and what the momentum principle would then say is, since I observe the object is not changing its momentum, I must have normal force plus weight is equal to 0. And that would allow me to deduce how the surface is affecting this object. For an object that's moving with a constant velocity, I've got the rate at which the momentum of the system changes. That's still something I've got to figure out. That's equal to the rate at which the momentum changes. The momentum is m times v, which is a constant. So the rate of change of momentum in this case is 0. It's the same case as the object just standing still. So again, I would have a weight downwards and normal force upwards, and if this is a frictionless surface, so no friction, then I would still have normal force plus the weight is the net force from the surroundings. These two cases exactly the same. What it shares with this going around the circle thing is we know, or deduce from the motion of the object what dp dt is. And from that, we figure out what the net, oops, not erase, I am highlighting. We figure out what the net force has to be.